Hello, this is a podcast from Engi 1331 for the NAE Grand Challenge, and our topic is developing methods for carbon sequestration. We are Nor Farisha Nor Osman, Alexander Mathin, Tuan Lee, Rayleigh Sims, Amanda Scudder, and Dat Tran. Our problem is to develop ways to get rid of excess amount of carbon dioxide from the atmosphere without causing any environmental damage. This is also known as carbon sequestration. Many countries today suffer from air pollution, and the main cause of this air pollution is from carbon dioxide emission. Our goal is to find a safe and environmentally friendly way to make this process both effective and efficient. Our code is used to help analyze carbon emission rates from around the globe, as well as from various centuries, in order to show the trend of carbon dioxide emission rates. We will be splitting up our code into two sections. The first section will be for loading the CSV file that the user has inserted into MATLAB, as well as analyzing the various features of that file. The second section is the actual code, which we will use to analyze the carbon dioxide emission rates using a variety of functions and cases.
For the algorithm and code logic, it focuses on big data analysis and flexible. The first step is configuration. It allows users to enter different file names, including combination of text and number. Due to big amount of the data, not all data is used for the output. So we only allow the user to select the column and range of the year that they would like to analyze it. So only the important data are processed. It will increase the efficiency and time. The code also recognizes the label of each kind of data and allow the user to re-enter the label of data. Make user easy to read the name, and it will not depend on the data file. Important thing is those configuration automatically save, so the next running will not need to redo any of those steps. After configuration, second function is overview and exporting. We allow users to overview the data file that they are selected. We think it's important because users need to overview the data to make sure that their data is valid in a short amount of time. And exporting the raw data with a complex state and number into the pure number data file is very useful. It allows the data run in different environments in the software, so the user they don't need to do it by their hand anymore. Next function of the program focus on the data analysis. The data analysis has two parts, visual and numerical. For the visual, user can view the data by graphing the line, graphing the percentage, and passing the reference to calculate the data and graph those calculator. For the numerical, the data will quick analyzing and finding the difference and comparing each type of data. It also gives the user the summary of minimum, maximum, and average. More advantage of analyzing our algorithm, read the old data and give the prediction of how the data will grow in the future in both visual and numerical. Although functions are independent, there is a menu that asking the user to select the function that they would like to do and allow the user to select again until they want to exit the program. And each function of the code is written in the different files, so the code is very easy to read, debug, and modification.
Hello, my name is Alexander Mathin, and I will be going over the first part of our code for the NAE Grand Challenges project. So I'm going to run this code here, and then we have our default configuration. The first section is basically when we load our CSV file, as we can see here, CO2 by source. Then we have all these configurations right here. Do you want to edit the configuration? No. Just want to leave it how it is. And now we have, the first section analyzes what each column is. So our first column is gas, second column is solid, third column is liquid. These are carbon dioxide fuel sources. You want to re-enter this? No. And then we have this whole menu of options. This is section 2. And I'm going to do section 1 first and see what happens. So 1 gets us back into the menu. basically show us what the options are again. And then we have part 2 here, CSV file information. If I click 2, it gives us all the information possible, number of locations, data titles, number of data, which is basically the amount of data rows there are, and available years are the years it goes from, the range of years.
Hi, I'm Amanda. I'm going to run through some test cases of our code for the NAE grant project. First, I'm going to run through case 4, which is titled Percentage Graph of Locations. So, run the code. We'll enter no for the first 2 prompts because we don't want to change the information that's already in there. We're given a menu option of the different continents. I'm going to select Europe. It prompts us to enter a value from 1751 to 2013. This is the starting year. I'm going to choose 1960. Then we are asked again to enter a value from 1960 to 2013. I choose 2000. These selections will output a pie chart that shows Europe from 1960 to 2000. It's pretty clear from the pie chart, the different things that make up this information, but it's displayed in the command window that Europe from 1960 to 2000, the highest consumption was 42.09% in solid fuels, and the lowest consumption was 0.34% in flaring. Case 5 is energy by location and year. So we input 5 into the command window's prompt. It brings us to a title list of the different fuels. So we have gas, solid, liquid, cement, and flaring, or like CO2 producers. We then are prompted to enter the coefficients of the 5 energies. I'm just going to put 1 for each one. We are given a menu option. I choose North America as the continent and the only continent. Just choose exit the menu option after that. I'm going to enter a value from 1785 to 2013. I choose 1800. We enter another value from 1800 to 2013. I choose 1900. This brings up a line graph, and it's obvious again that solid fuel is the largest energy producer for North America from 1800 to 1900. It is outputted in the command window. The overall highest energy produced belongs to North America is 10.28 tetradoules, and the lowest energy produced was from flaring and concrete, which had a value of 0.
Choice number 5 from the main menu, if picked, prompts the user to choose a continent, enter a 1x5 vector representing the energy coefficients for each carbon dioxide emitter, and finally to pick a date range based upon the location chosen. It proceeds to output the highest and lowest energies produced in terajoules and the type of carbon dioxide emitter. Choice number 6 prompts the user to enter a list of locations as well as a range of years based on the locations and a 1x5 vector of the cost per source of carbon dioxide, while outputting the money spent for each source. Choice number 7 asks for a location, range of years, and a 1x5 vector of CO2 produced per material, and outputs the total carbon dioxide produced for the provided locations and years.
Although the code work well, there are some limitations that we have to improve. First of all, because the program is based on a large database, we have to make sure that the data are correct, and when the user enter the file's name, they need to type in the correct format so that the code can run. Moreover, the configuration is quite complicated and sensitive. It is not easy for the new user to work with, but it is flexible and allows to run many of reported CO2 files as available. The program outputs the data which match with the information that the user chooses. This is what we expect in this project. This code will help us solve the issue of excess carbon emission rate by taking a large database and making it more accessible, easier to use, and much more direct. The prediction of carbon dioxide emission rate in the future can warn countries of what could potentially happen to the Earth's atmosphere so that they can take action before it's too late.